All right, we are now recording. Let's get the slideshow set up and maybe even turn on the projector. What you say, okay? And from current slide. And this takes forever to load. All right. All right, now we're in presenter view, so I need to get out of it and get into regular view. Yes, ma'am. Good morning. Yes, I know. Right after this class is over, I'm planning to come get it. Thank you so much. Okay. All right. I don't know if students can get flu shots or not. I know it's for faculty staff that we get it because we got our health insurance through the state. So you can check. I don't know. I doubt if it's available for students as well. Too bad. I think it should be, but they probably can't afford it. But maybe through your student insurance, I don't know. We'll have to maybe check into that. Okay. All right, the syllabus here. The only new announcement today, they're really looking for good tutors, and I know you folks will be great tutors. So if you're interested, they will pay you, okay, for tutoring. If you
student support service?
Yeah, student support services, yeah. If you made an A or a B in any course, doesn't have to be math, English, psychology, any course. If they need a tutor in it, biology, chemistry, they will pay you to tutor. And
I did that last semester.
You did?
Yeah, but this time I can't read that. I work during the Thursday, Friday, Saturday, and Sunday.
I see, yeah. So. And we're still recruiting for math team. And if you're interested in that, what I'm doing, I'm recording those practice sessions also. And it's under a, what do they call that? Playlist called Math Team, okay? So if you're interested in following just to see what it's like, I sent Dr. Thomas the link. I could get it for you. I just don't have it here. Big, long, hairy thing. So I sent her.
Was that a paper?
No, okay. What you do, the competition will be at Shelton State in October, the second weekend in October. I think it's a Saturday. And what you do, there's two parts to it. The first is the individual competition. They give you a, 30-question test, and you work it out, and they grade them and score them, and the top three get prizes. There's nothing for being in the bottom three or anything else, It's just fun. It's just, you get prizes if you get in the top three. Then in the afternoon, they have, or sometime later, they have the team competition. And then you work with a 4-person team solving problems, okay? And you do that. The morning, the first one is based on calculus, and the second one is based on pre-calculus. And then the top 3 teams get prizes. So it's just fun. It's just really good stuff. And what's more, I noticed one guy who's came yesterday afternoon is in Calculus 1 now. And we were going over Calculus 1 stuff that he hasn't had yet, but he was eating it up because this is all going, when he gets to it in his calculus class, he's already going to know it. So he's going to breeze through that part. So, and we'll be doing some Calculus 2 and Calculus 3 stuff, not a lot, but a little bit. So it would be advantageous to you. You can get to learn the tricks and the trades, early on. We do it Tuesday, Thursday afternoon from 3:30 to 4:45.
I love Thursday.
Okay. Okay, you so welcome to come, but like I said, I'll be recording them and putting them on the folder, and once you get the link for the folder, you can view any of the ones you miss. But you don't have to be there. Now, they also have practices on the Birmingham campus. I know Miss Geraci is doing on Monday, Wednesday afternoon, and Miss Martin is doing Monday and Wednesday before her class. So, in fact, the guy who came yesterday, he's in her review before her class. He has her class, and then he comes over here for the practice here. So you can do it.
Miss Martin told me the Muhammad that you're looking for, he in trade.
Who is this?
Muhammad.
Yeah.
He's in trade now.
Oh, is he?
Yeah. So she told me he's not supposed to be in this class, and he in trade class.
Why in the world did he sign up for this? Muhammad.
He's the only Muhammad.
Javu.
Yeah.
Okay.
He's the only Muhammad we have.
Okay.
I know him. I met
Yeah.
him in the accident.
Uh-huh.
So she said he's in
Trig class. Okay. Well, then he's not in this one anymore. He hadn't paid for this one, so maybe he just misregistered for it incorrectly. So it's not going to cost him anything. All right. Good deal. Any other questions? Math type questions or any other questions? All right. Then we're on average value. This is in section 6.2 on page 345, right at the bottom of the page. It's just a very short thing there before we do. I think we started this last time, didn't we? Didn't I ask the question, what if you had 3 tests? And I said, what's your average? How would you determine that? Add them together? 3, yeah. Okay, exactly. That's how we do average value. Okay? Average value would be done. Oops, I forgot to get the pen. Okay, in this mode, it's not going to let me access a pen, so I'm going to have to do it this way. Sorry. Takes a bit longer, but I can do it. Okay. I'm going to call it A average. The bar over it means average. What that would be is A1 plus A2 plus A3 plus ... all the way up to A sub n, and we divide it by n, where n is the number, and I guess they did that to be a capital N. I'm trying to just get it the same way the book does. Okay, A sub n. Just like you do, okay? Now the other way to express this is 1 over n times the summation from I equal, are they using I? No, they're using j. J equal 1 to n of A sub j. Okay? That's the other way to express it. Okay? Now these certainly wouldn't be your test scores, but this might be, quiz scores or something like that. Say you had an 18, a 25, a 22, and a 31. Okay? What's the average of those? Well, what we would do, add them together and divide by 4. Perfect. Okay? Now let's see. Let's add those together. 25 and 22 is 47, and 31 is 78, and 18 would be 96, I think. Okay, that would be 96 divided by 4, and that would be 20. Say again? 24. Perfect. Okay. So that's the average value of those. Okay. Now, we know how to do that for discrete numbers. That's what we've just been doing, discrete numbers. What if we had a continuous function like that? How do we find the average value there? What we could do is pick a certain number of values, like split this function into n subdivisions. Okay, there will actually be n plus 1 points. You'd have this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to n. And then you would sum all those together and divide by n, just like we did. Okay? Might help if I blew this up a little bit. Trying to cut out as much of the writing as I can. Okay. All right. So if we had a continuous function here, that wouldn't give you exactly, it would be an approximation of the average value. Okay? Just pick these points, x0, 1, 2, 3, 4, up to x of n. That's n plus 1 points. That's n plus 1. Okay? And add them together and divide by n. That's one way to do it, okay? But there's actually a better way than that, and unfortunately, it's not showing up on the slide. So what I'll do is get out of that, and the average values of f of x at those points would be equal to, now, do you remember this notation? Capital R sub n? This is from back probably in Math 125. That would be taking the right-hand points and taking those n right-hand points there. So there they would just do n. They wouldn't do x sub 0. They would do the right-hand and then divide that by the length of this, b minus a, okay? That would be another way to do this, okay? Because the total length of this would be b minus a, that would be the length of this divided by the functional values, and that would be it. That's the right hand. Now, if you let the n approach infinity, then you're getting the points closer and closer and closer and closer together. So basically, you are getting the average of all those. And the difference here would be how far it is between those 2 points. So that sure enough would work in the limit. Okay? So, if that's working in the limit, here is your definition that we go by. I hope this won't cut off. Yes, it does. Yeah. Okay, average value. The average value of an integrable function, it has to be integrable or else this doesn't work. What we do, rather than a summation, make that an integration, and it'll be the integral of alpha of x dx, okay, divided by the length of x, b minus a. Okay, so this will be the, if you think of it, let's go back to that previous slide, and this will, of course, drop. The integral from b minus a of alpha of x would be the area under that curve, wouldn't it? That's what integration does for you. Divide it by the length, and that gives you the average height of this. Because what is an area? It's a length times a height. Width times height, okay? And if you divide by the total width, that gives you your average height, and that would be the average value of the function. So sure enough, that seems like a reasonable thing to do, okay? But it has to be integral over that interval. And what does that mean? If this function has a discontinuity, it can't happen between a and b. Because you can't integrate over a discontinuity. That's why it said integral function on that interval. Okay? It may have a discontinuity somewhere you're not doing. If you're going, if it has a discontinuity at 0 and you're only doing from 1 to 7, no problem. As long as it's integrable there, then you can do the calculation, and then you divide by 6. 7 minus 1. Okay? That gives you your average value. It's a pretty straightforward concept. Okay? The average value of a function is also called the mean value. Okay? And I can't tell, is this the... I think this is the graphical insight. And of course, when I blow this up, it's going to cut some off. So I'll try to protect as much of it as I can. All right. The area under this curve, y is equal to sine x. Okay. And they're only doing from 0 to pi. Why is that a good choice here? You could have had something smaller than that. But that's about as far as you want to go, because anything beyond this, your area is now going to be negative. And anything beyond this, your area is going to be negative. So you'd have that to fiddle with. Usually we keep this in positive, okay? And we'll do the integral of that, sine x, okay? The area under the graph is equal to the area of a rectangle whose height is that average value m, okay? And sure enough, graphically, that looks about right. The space up here should be equal to the space here. This overshot, this undershot, those should equal out. Okay? Now, how did they get that? Well, of course, as soon as I go to right, it's going to. Okay. I thought maybe the pen will come up, but it isn't. So I have to do it this way. Wait. Yeah, I can do it right there. What we have is the integral from where to where? To 0 to pi. And watch. So this out front is going to be pi minus 0. So that's just going to be pi. Now this is going to be your average value. Okay. And then what's your function? Sine x dx. Okay. All right. This will be 1 over pi. And what's the antiderivative of sine x? Negative cosine x. Okay. Evaluated from 0 to pi. Okay. It's 1 over pi. Now, what is cosine of pi? Negative 1, and you have a minus sign in front of it, so that makes a 1, minus the minus sign, that makes it plus cosine of 0. Huh? 1, okay. So this gives you 2 over pi. And that's where they get the average value is 2 over pi. Okay? Which is approximately 2/3, right? Because pi is 3.14, so it's a little bit less than 2/3. And sure enough, if that's 1 up here, that's the maximum value of this. 1/3, 2/3, that's about right. And that's a really good approximation of what the average value of sine x is between 0 and pi. Okay? Does that make sense?
How did you get 1 over pi from? Can you explain?
Okay. Here's how you do it. The formula is the average value is 1 over b minus a times the integral from a to b f of x dx. Okay. So since our interval was 0 to pi, that was pi minus 0. Good question. All right. Any others? Okay. Now, I think we just did example 7. It was your graphical insight, but it's also was example 7. And the average value certainly has to be something between 0 and 1, because all the values were between 0 and 1, and that is. They gave the estimation of 0.637. Like I said, a little bit less than 2/3. 2/3 would have been 0.666667, and this is 0.637, so pretty close. All right, and then the next is sort of an interesting little problem. And why they have the cute little picture here, I'm not sure. It doesn't add much to the math, but it is a cute little picture. This is something called a bush baby. Okay? Sounds a little strange, but I think it's Australian, or is it African? I don't remember where. They don't say. It looks Australian to me, but it could be from anywhere. I don't know. Bush baby can jump as high as 2 meters. That means its center of mass rises more than, it cuts this off, 5 body lengths. Okay? Now, if I could jump 5 body lengths, okay, that would be, I'm pretty close to 6 feet. 6 times 5 would be 30 feet in the air. Sign me up, okay? That would be really. By contrast, Michael Jordan rises at most 0.6 body length when he executes a slam dunk. Interesting that the new edition of the book has Blake Griffin. Michael Jordan was back in my generation. Blake Griffin, I guess, is someone who's a good. Is he a center or a guard or power forward? Okay. For whom? Who does he play for? Oh, does he? Okay. Okay. He rises at most 0.6 of his body length. This baby here can do 5 times his body length. Okay. So this is example 8. The bush baby, Galago, whatever that is, Senegalensis. Actually, when I look at that name, I wonder if they're from Galapagos Island. That's where a lot of really bizarre animals live. Island off the coast of South America, the west coast of South America. I think it's west coast. And it's just incredible, the animals that live there. I mean, it's been separated from the rest of the world, and they just developed a whole different set of species, And so I wonder if he's from there, just from the Galago being his first part of his Latin name. Small primate with remarkable jumping ability. Find the average speed during a jump if the initial vertical velocity is, so v sub 0, of course when I go to write this is going to shrink back again. I don't think I need that. V sub 0 is initial, close up there. V sub 0 is 600 centimeters per second. Now that's fast. You have to be fast to jump that high, okay? Use Galileo's formula for the height, which is h of t is equal to v0t minus 1/2 gt squared. Is that how they write it? Yeah. Now, since you're dealing the height in centimeters, okay, then your g has to be in centimeters per second squared. What do we usually use g as? Meters per second squared, and what is that number? 9.8. 9.8 meters per second squared. To get that to centimeters, you just multiply, by 100. okay, because you're going from meters to centimeters, and that's 100 centimeters in 1 meter. The meters cancel out, and that gives you 980 centimeters per second squared. So that's the G that we'll use. Okay? Now, find the average speed during the jump. Okay? Now, I don't think these are physicists, because the way they do this problem to me is rather bizarre. Okay, but it's fine, it's correct. Okay. Okay. So your equation here is h of t is equal to 600 t minus 1/2 of 980 is 490 t squared. Okay? Now, so the height, of course, would be 0 at t is equal to 0, because when you start, its height is 0. And then where he lands again. Okay? So when that he lands again, that would give you 0 is equal to 600t minus 490 t squared. Okay? Well, let's factor out as much as we can. I'm going to get rid of 10, just like that. And then I'm going to move things to the other side. 49t squared minus 60t is equal to 0. Okay? Factor that, t times 49t minus 60 is equal to 0. So we already know t is equal to 0. It's going to be 0 there, but the other is 49t is equal to 60. So t is equal to 60/49ths of a second. Okay, which means a little over a second. Now, that's how I would do it. They say 6 over 4.9, which is the same thing, but why? I mean, I don't know. Maybe indicating it's close to 6/5 of a second, but not quite. So, those are his times. What is his velocity? Well, that would be derivative of h. So h prime would be 600 minus what? Take the derivative of that. (980) t. Okay? Solve for, let's see, do we need that? I don't guess we need where it's equal to 0. So that is its velocity. Okay? Now, that's what we're trying to find the average value of. So then to get the average value, V bar is what I'm going to call it, that would be 1 over this interval, 1 over 60 divided by 49. Well, we know what that is. That's 49 over 60. So I'm going to, I hope it's all right to do that. It's just a lot. It makes more sense to, yeah, this thing's jumping all over the place. Okay. To write this is 49 over 60. Okay. That's 1 over 60 over 49, which is 49 over 60 times the integral of this thing. Okay? And you're going from 0 to 49/60th, right? 600 minus 980 t dt. Now, a problem with that, they put it in absolute values, okay? And okay, here's why. I should have done this on the next slide. Okay. This is actually a graph of that velocity, that speed. Okay. When the thing is jumping up, it has a positive velocity. Initial speed, 600 centimeters per second. That's what they gave us. As it's jumping up, when it reaches its max, now after that, velocity is going downward. Okay? So that's negative. So the speed is the magnitude of that velocity, so you do here. So that's why they use the absolute value function. Okay? Now, what you can do is do this triangle here and double it, because you know that's got to be exactly the same, because the speed is linear. Okay? So that's how I would do it. Just do the first part of this, and that would be from 0 to half of 60 over 49, and that would be 60 over 98. So that's where we're going to stop it right there, and then double that amount. Now, they go through this other rigmarole to get it, but anyway, that gives you the average speed. Okay? So, like I said, I wish I had done it on this page. I use V-bar. I happen to notice here they're using, I don't think I need that. They're using S-bar. So to get back on the thing, I put V-bar, this is S-bar, whichever you want to do it, okay, is equal to, because it's average speed. Remember, we had 49 over 60, okay, when we redid this. And the integral was now going to be, like I said, let's just go from 0 to 6 over 60 over 98. 0 to here, 60 over 98, which would be 30 over 4.9. 49, I'm sorry, 30 over 49, okay? And then we'll do that, well, why do an integral, okay? Yes, it works, but that's a triangle, okay? That's 1/2 the base times the height. We're going to double that, so that's just going to be the base times the height. So it's going to be this length, 6.8, times that height, which is 600. That's going to be your answer. So why go to all the effort to do it? I guess to practice your integration, maybe, but y'all can do that. Let's see if we don't get the same answer. This part's the same, but this is going to be the base times the height. The base is 60 over 98 times 600. Okay, that's the height of that triangle. Okay, and this is going to be 36,000 divided by 98. So if you got a calculator, plug that in, see what you get. Okay, say that again. 7273. Okay. Now, we've got to multiply that by, and I wish I had done this. Forget that for right now. Multiply this by 49 over 60, okay, because that was what we were doing that. Well, this will go into there twice. This will go into that exact. So this will be 300. Boy, why did I do all that? 300 centimeters per second. Which is, guess what? Exactly half of its maximum speed. The speed is linear, right? So the average between 600 and 0 is 300. And the same thing, 0 to 600 is 300. So yeah, its average speed is 300. Why go through all that work when it comes out so simply? You can do it. It works. Knock yourself out. It works. Okay. Now, there is an important difference between the average of a list of numbers and the average value of a continuous function. If the average score on an exam is 84, the 84 lies between the highest and lowest scores. But it is possible that no student received a score of 84. Now, by contrast, the mean value theorem says that if you do have some sort of a graph here, then you're going to have at least one place where that is the same. Of course, with scores, those are finite numbers. Those are discrete numbers, and the average may not be one of those numbers. But if you've got a continuous function, your average has got to be somewhere in that place. So mean value theorem tells you that has to be the case. So some places going to have those average values. So let's go back to the sine function that we did before. Okay. All right. Function f of x, this is, well, it may not be the sine function, but it looks just like it. Okay. Function f takes on average value m and actually has exactly that value at two different places. Is that always the case? If this was a strictly increasing function, no it wouldn't, or strictly decreasing function, it would only intersect once. Since it goes up and comes down, generally that will be twice. But it could have been more than twice. If this function would have been, it could have had several places. But the function f takes on the average value m at points where the the upper edge of the rectangle intersects the graph. And it could be in more than one spot. Okay. That leads to this theorem. Mean value theorem. My head is clogging up like crazy. I don't know why. But I'm having trouble talking and breathing even. So sorry about this. Mean value theorem for integral. If f of x is continuous on some interval a to b, there exists some value c that's in that interval a to b such that f of c is exactly equal to the average value, 1 over b minus a, f of interval from b, a to b, f of x dx. F of x is continuous, then this will be the case. It may actually be more than one location, but it will be at least one location if it's a continuous function. If it had a discontinuity, yeah, it could fall in there, but this is a continuous function. All right, and they do a little proof there, and I think that's probably the end of the section. Okay, so let's go back, and I'll use this page. The 6.2 had formulas for volume, total mass, given densities, total population, given radial densities, laminar flow rate, given velocity, and average value, given the function, of course. Goodness, I can't breathe. I'm so sorry. Let's look at the preliminary questions. What's going on there? At the top of page 348. What is the average value I don't know why I overlined the average value of f on the interval 0 to 4 if the area between the graph of f and the x-axis is equal to 12. Okay, what would be the average value? Any ideas?
Do we still have to use the same formula?
Yeah. Basically, yes. Kinda, yes. Okay. What was that formula? Well, there it is right there, isn't it? Well, no, it isn't. That's mean value theorem. Yeah, well, that's what it's asked for. Average value, mean value. Okay.
So it's going to be 1 over 4, right?
Yeah, 1 over 4.
And
0 to 4. But we don't know the function. But they told us the area between the function and the x-axis, that's exactly what this is, isn't it? This is the area formula. So if this is 12, and this is 1 over 4, the average value would be 3. That's all there is. You don't actually need to do an integration. They told you enough to get by without it. Okay, and this is 12 point, no, in the wrong section. 6.2, preliminary question 3. Perfect. Okay. All right, the second one. Find the volume of a solid extending from y equal 2 to y equal 5 Okay? If every cross-section has an area A of y is equal to 5. A of y equal to 5. Okay? What do you think the volume of that would be? Say again?
I'm not sure it's right.
Yeah, here.
I guess it's 1.6.
No. Okay. Okay. Now for cross-sectional area, this isn't this. Okay. Cross-sectional area, the volume formula this is on the previous page if you want to turn back and see, v is equal to integral from, second, a to b, the area of y, dy. Okay? What's your a to b here? 2 to 5. And what's your a of y? 5. So it would be 5y. Y calculated from 2 to 5. 3 times 5 is 3 times 5, not divided by. 15. That would be 15. Whatever your volume, volume units would be. Cubic whatevers. Okay?
So we don't get the 1/3 in front.
Okay. No, this is for average value. This isn't volume.
Okay.
Yeah. Volume is just, yeah. Yeah. So this would just be 5. You can pull that outside. This would be y evaluated from b to a. That would be 5 minus 2. That's 3 times 5 is 15. Yeah. Okay. Yeah. Or the other way to look at this, every area here is 5. Now it could be doing all this stuff, but all the areas are 5. Okay? And you got a total height of 3. From 2 to 5. 5. Yeah, volume is area times height. Area of the base times the height. As long as all the areas are the same. And they told you it was. Okay? Or you can do the calculation. Okay? The next, what is the definition of flow rate? And basically, definition of flow rate, just turn back and see what the definition of flow rate is. The volume per unit time of a fluid passing through a tube. Okay? Hopefully that's all they're looking for. Flow rate is the volume of fluid passing through a cross-sectional area at a given point per unit time. Flow rate. Number 4. Which assumption about fluid velocity did we use to compute the flow rate as an integral? Which assumption about fluid velocity did we use to compute the flow rate as an integral? Okay? If you flip back to that, okay, it's basically the definition of laminar. We're assuming it's laminar flow. And they give that by which we mean that the velocity v of r depends only on the distance r from the center of the tube. If you had turbulent flow, you could have eddy currents in there and velocity would be wacko. It'd be all sorts of different things. So we're assuming laminar flow. Now that's the only assumption I have. The fluid velocity depends only on the radial distance from the center of the tube, which is the definition for laminar flow. Okay, now number 5. The average value of F on 1 to 4 is 5. Find the integral of 1 to 4 f of x. Okay. We can use this one right here. Okay. This f of c is your average value, mean value, whatever you want to call it. Okay? And they tell you right here that is 5. So 5 is equal to 1 over, and what's your b minus a here? No, 4 minus 1. It's 1 to 4. 3, so that would be 3 times the integral from 1 to 3. No, 1 to 4, sorry, 1 to 4, alpha of x dx. That's what they're looking for, okay? Can you calculate it? It's almost like deja vu all over again. They told you the average value is 5. They told you you're going from 1 to 4, so that made this 1/3. This is the integral you're looking for, which is the integral from 1 to 4 alpha of x dx. That's what we're looking for. Can you give it to me? Solve for this. This like you're a null. Why? Okay? 5 is equal to 1/3 of y. What's y? Second? What's that? Yeah, this is your y. And if you said 5 is equal to 1/3 of y, what would y be? Solve that simple equation. Multiply both sides by 3. 15, okay. That's all. It wasn't anything hard or difficult. It was actually.
So what happened to the interval like 1 to 4? What's going to happen with that?
Yeah, here I wrote down 3. I meant to write down 4. 1 to 4.
Yeah.
This is 4 minus 1. That's where you got your 3. Okay. But they gave you everything but that. It's easy to calculate what that is. Yeah. All right, homework exercises here. I think I gave you some of these before. Any of the odds 1 through 7. Any of the odds 9 through 13. Sorry about that. Any of the odds 15 through wow, there's a whole bunch of these. 37, yeah, I think I gave you that before. Then any of the odds 39 to 47, and then any of the odds 49 through 61. Then I would try 63, and you can look at 65. That's just working out on paper. Okay, and then further insights would be 67 if you want to take it. You don't need to. Any questions on that then? All right. I think this then is the end of section 6.2. What we've got to do now is go to 6.3. Volumes of revolution. Okay, we're going to have some revolutionary volumes here. Okay. It's going to take a while for PowerPoint to load. This is the slow part. And I'll set up my slideshow. And we got to wait. Okay. Then it gets in presenter view that I have to get out of. And then I have to get back in a view we both can see and write on. Okay. We have it. It was set up fine and then it shifted over. I don't know why it does that. Let's see, I don't think I can blow this up enough to make it make sense. Okay. Yeah. Yeah, like this. Yeah, I was going to start with this. Okay. Sorry. A solid of a solid of revolution is a solid obtained by rotating or revolving a region in a plane about an axis. Now, it doesn't have to be a coordinate axis, just any old axis. We're going to start with the coordinate axis. Okay? The sphere and right circular cone are familiar examples of such solids. Okay? So here is a line, a straight line. That's all it is. Crosses the y-axis at its y-intercept. That's where it starts and ends at the x-axis at the x-intercept. That line segment there. If we revolve that around the y-axis, you're going to get a cone, because revolving it takes it around an axis, which means every point here goes around the y-axis, because that's the axis we're using here, and they all cut little circles, right? Including the bottom, that base cuts a circle. So whatever your x-intercept was here is going to sweep that all the way around, so your y is going to go to minus that value, whatever that value is. Okay? And you're going to get a cone like this. All right. Oh, man, I'm stiff. Now, what if you had a semicircle that's the function, that's the semicircle, and revolve that around the x-axis, okay? Then you'll get a sphere, okay? Goodness gracious, that's so bright, it's hard to see. You get that sphere of revolution, okay? Now, they drew a circle here. That's perfectly correct, because you do have a circle there, but I would have called the circle in here, because that's the one that you traced out when you're revolving this around the x-axis. But it's a sphere, okay? So those are examples of solids of revolution. Now, those each use a coordinate axis, different one. You can use that or some other line. You just need an axis of revolution. Now, where we're going to start here is assume that your f of x is always greater than 0 between the limits, a and b. The interval that you're doing around, we're going to assume that's always positive. If it went negative, then when you did an axis of revolution, you'd be sort of cutting out a hole somewhere in there. We're not going to do that. We're going to have just a solid, okay? It never goes negative, okay? Between a and b, x between a and b. The solid obtained by rotating the region, under that graph of f about the x-axis has a special feature. All the vertical cross-sections are circles. Okay? Now, when they say vertical cross-sections, they mean the cross-section this way. If you revolve this around the x-axis, then all the vertical cross-sections are circles. This will be a circle of that radius, a circle of that radius. Well, of course, with a sphere, you've got that. And I would draw it here. In fact, I already said it here. Oops. Okay. But this one you're revolving around the y-axis. So then all the circles this way, all the cross-sections this way are circles. Tiny little circles up here, big circles here, every circle in between. Anytime you revolve anything around an axis, then at any point with that, you're going to get a circle around that point, around the axis there. That's what a revolution is, going around in a circle. Okay. Now, the area of then any vertical cross-sectional area would be your pi times r squared, where r is whatever that f of x is. Okay? If this is your f of x here, okay, you're revolving that around the x-axis, your radius is going to be your y value, y of x. So it would be pi times that y of x squared. Okay. Or f of x squared. So let's go to another one. gracious, I'm sorry about my head. Breathe. All right, here we have any old function f of x here, between some values a and b. F of x is always positive in that interval. Down here somewhere it might go negative, up there it may come down and go negative. We don't care. In this interval it's always positive. When you revolve this function about the x-axis, then you're going to get, for every value x there, that's going to form a perfect circle. Okay? And the area of that circle is pi times that f of x squared. Okay? A book likes to call this f of x squared. I like to say f squared of x. To me, that's clearer and cleaner. Okay? But if you were to revolve that entire segment here from a to b around the x-axis, you get something like that. Now, to me, that looks like a wash tub set on its edge. Okay? But that's just me. I grew up on a farm. Okay? But that's what you have there. And if you're doing the volume of that solid of revolution, what we just said, every cross-section is a circle. Pi alpha of x, or f squared of x, okay, times your dx as you integrate from a to b. There's your formula right there. They are going to walk you through all kinds of lengths of it, but there it is, okay? And here is, and this is called, by the way, the disk method. The reason they call it that, every one of those little cross sections that we had was a little disk. Okay? Volume of revolution, the disk method. If f of x is continuous, now that's required, and f of x is always greater than or equal to 0 on the interval, then the solid obtained by rotating a region under the graph about the x-axis, with the r being f of x, this would be, the volume would be pi times the integral. This is going to be your limits on x, a to b, dx. That's going to be the thickness of your washer or your disc, pi r squared. At the area of that disc, that r is f of x, so that'd be pi integral a to b of f of x squared. Now, see, they put the square out here. I find it cleaner looking to put f squared of x. It's the function being squared, not the x. Of course the x isn't being squared. That's what it sort of looks like. So I like to do f prime of f squared of x dx. There's your volume of a solid of revolution. Yeah. All right. So, actually go further that way. Okay. I think we're ready for example 1 then. Here's example 1. This will disappear as soon as I think this will work here. Okay. Calculate the volume V of a solid obtained by rotating the region under y is equal to x squared, and that's this parabola here. Now they have really done some monkeying around with the scales here. Okay, they're showing this to be 2, so that would be 1. This would be 1. So they've really distorted the scale pretty badly. Expanded the x and contracted the y. Normally, if you looked at that, it goes like this. They've really contracted, compressed the y, and expanded the x. Okay? But that, as long as you understand they've done that, that's what we've got here. And again, this function, y is equal to x squared, from 0 to 2. So this value up here is actually 4. Okay? And that's less than 2 here, so that's why I say they've done that. This is what you're dealing with. One of the problems with my clogging up, this is blowing cold air right on me, and for some reason that's just closing my head up. Okay. So there's the problem. They drew it for you, okay? Hopefully with that, you can do what they're asking for. Calculate the volume obtained from rotating that area, y is equal to x squared, about the axis from 0 to 2. X equals 0 to 2, which is what they show here. So, okay. What would that volume be? Oh, I've got to get all this back. Sorry about this. There we go. So the volume would be what? Pi times the integral from 0 to 2. This is on dx, so I'm going to put the dx out here. That's your x variables. X squared squared. Okay? Pi r squared. Pi y squared. Y is x squared dx. Okay? Now, that would be pi times the integral from 0 to 2 of x to the 4th dx. X squared squared is x to the 4th. That's an ugly looking 2 up there, but okay. This would be pi times, what's the antiderivative of x to the 4th? Over 5, evaluated from 0 to 2. That would be pi times 2 to the 5th. 2, 4, 8, 16, 32. Just double every time. So that would be 32 fifths minus 0 fifths. I'll do that one. Okay. So this gives you 32 pi fifths. Okay. However they write it. 32 fifths pi is how they do it, rather than 32 pi over 5. And it doesn't matter. 32 fifths times pi. Whatever. They're all numbers. It doesn't matter what order you do it. Now, there's some useful variations on the formula for the volume of revolution. First, consider the region between the two curves. Y is equal to f of x, and y is equal to g of x. So not just that you have one function, but you have two functions. Okay? Where you always want f of x to be greater than or equal to g of x, but g of x itself is always greater than or equal to 0, so it can't go negative. Okay? When that region is rotated about the x-axis, the segment AB, which we're not showing here, sweeps out a washer portion shown in 5B. Let's go on and get that. Okay. I'm going to come back to this one. Okay. Here's what we have. This is what they've been talking about here. Okay, I went a little too far on that one. Sorry.
Do you want some water?
I think I need to go clear my head.
I have a bottle.
But I don't think you want to drink after me. So no, I need to clear my head too. So I'm going there and down. I'm going to turn this off for just a minute while I'm going to do that. And I'm going to stop the, all right, we're coming back, but it's going to take a while for the projector to come back. But what we've got here, we're on the sort of the beige box right in the middle of page 352. So what we have here is two functions, and as soon as it comes up, yeah, here. I wish they showed the picture first and then this, but this is, in fact, let's do it that way. Here's what we've got. Okay. Okay. We'll start here. Here we have two functions. Notice, f of x always greater than g of x, greater than or equal to, this is always greater than. G of x always greater than 0. Okay, so two functions up here in the first quadrant, but they don't have to be in the first quadrant. They could extend over here, but they just got to be greater. Okay, from a to b, at least these two functions. Okay, this function g of x goes negative somewhere out here. The region we're interested in, it stays positive and is always less than f of x. Okay, so here's what we got. We're going to rotate that region around the x-axis. Okay, and that's going to give us what's going to be the third figure here. But let's start with just this part, a to b, rotated around the x-axis. That's what gives you this washer. That's what we were talking about, the washer method. It's like a disc, only it's got a hole in the middle. Okay, so basically, and if you think about this, the area of this blue part here is the area of the big disk, f of x, pi f squared, minus, cut out the hole in the middle, and that's pi g squared. So the pi's can come out on the outside. That leaves you the difference between f squared and g squared. Okay? And this is what you've got there. It's a stopper with a hole in it. Okay? Like they use in chemistry labs. Okay? 0 going from a to b. You're doing your dx, so that's going to be the thickness of your washer. And then you're going to have the outer pi times the outer squared minus pi times the inner squared. Okay? And that's where they get this one. Okay? See, it seemed like a little crazy they had it out of order. So your volume of between two functions, f and g, pi times the integral from a to b of r squared outer minus r squared inner dx, where the r on the outer is f of x, f squared of x, minus g squared of x dx. And that gives it to you. Okay? Disk is just one. The washer is f squared minus g squared. Okay. I think that puts us ready for example 2. And I think this is the figure for example 2. Okay. Bless you. All right. Find the volume V obtained by revolving the region between y is equal to x squared plus 4. That's the upper curve there. And y is equal to 2. That's the horizontal line here. X squared plus 4 intersects this at 4 and goes up there. By the way, that's going, just to get the thing, it's integrating from 1 to 3. So at x equal 1, this will be 5 here. At x equal 3, that would be 13 there. So you see, again, they've expanded the x scale and compressed the y scale. So this isn't how it would have looked if I would have graphed it, okay? And that gives you the megaphone or Christmas tree stand or something like that that you have over there, okay? And your finding the volume between 1 and 3. So 1 less than or equal to x less than or equal to 3. So how would you set this up to do it? Formula V is equal to pi. Good start. The integral from 1 to 3. X squared plus 4 squared minus 2 squared. All that is times your dx, sorry, because x is. Picture this, you're splitting this, cutting this into little slices. Every one of those slices is a little washer, and the dx is your thickness of that. Your area is the outer squared minus center squared. Yeah, pi times that. Yeah. So, first step, I would say, let's square that binomial and do whatever we need to it. The pi times the integral from 1 to 3. Okay? And what would that be? X to the 4th plus 8x squared is what you said, right? Good. Plus what? 16, is that what I heard? Yeah, 16 minus 4 would be 12. Is that what you got? Okay, dx. He's ahead of me. Okay? Now, let's do the integral. That would be pi times x to the 5th over 5, or 1/5 x 5th, plus 8/3 x cubed plus 12x evaluated from 1 to 3. Okay? This is the hard part, okay? Not hard, but it's just pi times 3 to the 5th. Well, 81 is 3 to the 4th, and times another 3 is 243, right? Is that right? Okay. 243 over 5 plus, and 3 cubed is 27. Okay, but 3 will go into 27 9 times, so this will be plus 72. Plus 12 times 3 is 36, minus 1/5, minus 8/3, minus 12. You buy that? Is that what you're doing? Okay. Now let's see if we can make any of this make any more sense. Not a lot. Okay. Let's subtract our fifths first. And this will be pi. This is all an exercise in fractions, okay? This is 242 fifths when you subtract out the 1/5. And let's add those other, well, let's just subtract 12 from 72. That would give you 60 plus 36. That's plus 96 minus 8/3. I think I've gotten everything in there, right? Well, we got to get least common denominator, which is 15. So this is going to be pi times 3 times that is going to be 6, 12, 726, I believe, over 15, plus, oh boy, someone do 15 times 96. Second? 15 times 96. Huge number. Okay, say 1, 4, 4, 0. Okay. All right, good deal. Okay, over 15 minus 40 over 15. Right? Okay, the 40 over 15 wipes out the 40 there. So you got pi times 2126 over 15. All right. Now, let's see. Is that the answer? Yeah. I was trying to see if we could reduce it any. So this would be, do they write it this way? 21/26 pi. Yeah. I love it when they have such nice round numbers. Don't you? Yeah, 21/26 pi. Good deal. All right. Now, ready for the next one? All right. Here's the next one. Blow this up some too. Okay, we got a clock watcher already, huh? No, okay. What you got? 05, okay. All right, we got 11:15. We got 10 minutes, right? 11:10, you're right. 5 minutes, sorry about that. I think we can get this one done. Let's try it. Revolving around the horizontal axis. That's what we've been doing. But it's one not the x-axis, okay? So this might take a little more time. Find the volume V of the wetting band, and this is really how these are shaped. Most of the time they're curved on the inside, but also curved outside, also curved a little on the inside, and then revolved around. So that's why they call it a wetting band. Obtained by rotating the region between the graphs of f of x equal x squared plus 2, that's the lower blue line here, and g of x is equal to 4 minus x squared, that's the upper, or the outside of that curve, okay? About the horizontal line, y is equal to -3. Not the x-axis where y is equal to 0, but y is equal to -3. Okay, now in this case, we could have had this B curve being less than, we could have had something less than, you could have had a negative number here, as long as it's not below -3. So you could have done that. They didn't. They kept it all positive, but you wouldn't have to, as long as nothing breaks the axis of rotation. Okay. Now, they've already set it up for you, but you really need to know how to go. Most of the time on a test, it's not going to be set up for you. You got to figure it all out. So the first thing you got to do is find out, what are the limits on this? They've shown you, it looks like the limits. You need to verify that for yourself. So how would you do that? Second? Okay, that's what it sure looks like. Do you know that for a fact? That's what the picture looks like. How do you verify that? You see where those two functions are equal to each other. So we say, and of course I'm going to shrink back here, 4 minus x squared equal x squared plus 2. How are we going to solve that? Let's get everything on one side or the other 0 on the other side. So I prefer to add an x squared to both sides. Okay? And if we do that, then let's subtract the 4 from both sides. Okay? And that will give me a 0 over here, which is what I want. And this will be 2x squared minus 2. Which now we'd go into, what's the F word? Factor. Okay? When I ask for it, that better be what it is. Okay? That's going to be 2 times x squared minus 1. And guess what that is? 2 times x plus 1 times x minus 1. And set it equal to 0. Certainly 2 can't be 0. So that's not an option. Divide that out. So x plus 1 equals 0. That'll be x equals negative 1. And x minus 1 equals 0 will be x equals 1. So yeah, those are the limits on x. Plus 1 to minus 1 to plus 1. Okay? So we've got that. Now what we've got to do is do our function. Okay? Well, the upper function in between those is always going to be your g, not your f. So don't get that cross up. G squared minus f squared. But I shouldn't have said that, because your radius now, you're going around this line, so it's this function that's 4 minus x squared minus a minus 3 or plus 3. Okay? That's your first radius, right? And your second radius is this one, x squared plus 2 minus a minus 3 or plus 3. That's your second radius. And those are what you're squaring, not the other thing. Now, are we out of time or not?
Yeah.
We are? We still got a minute.
It's
It's 11:10?
Yeah.
Okay. I was afraid with that description we weren't going to finish, and we didn't. Okay, so we are going to pick up with example 3. We may see how much you remember next time. Let's see, did we get enough covered here? Yeah, this is a short section. I think you can do either 1 or 3. I think you can do any of the odds 5 through 11. I think you can do 13. I think you can do any of the odds 15 through 19. And we'll stop there. We'll pick up the rest of those next time. Okay? So we'll begin with example 3. Now, let me try to remind myself. Didn't I give you all a test on, chapter 5. So you got that to work on too. And we missed Theo today. And Muhammad, we think, is not in the class. Okay, good deal. All right, good deal. We will catch you. Have a good weekend working on calculus. That'll make it good, and we'll see